So good evening everyone. I am Pawan Kumar Sak, PhD scholar from IIT Kanpur. I am the TA for the course of Elements of Solar Energy Conversion. So this is the fourth week where I will discuss some problems and also some concepts related to the shading and some sign conventions for the different angles. Okay. So first I will discuss the sign conventions. For different angles. Okay. So the first one is latitude angle. I expect that you have already known about this latitude angle, but still I will draw and will try to explain what is this mean. Suppose, sorry, this is okay. Now it's better. Okay. So suppose this is the center of the Earth, that is C, and take any point or location on the surface of this globe. Okay. Suppose this is the position. Also, this is our equatorial plane. Now, if we plot the uh, projection of this location, suppose L, suppose some other points I'm using like A. Okay, if we plot the projection of this location A on the equatorial plane. Okay, so let's suppose this is the projection A dash on the equatorial plane. Then if we will connect the observer location with the center, then the angle between the projection and the location of the observer, this is the angle that is making between the projection and the location that is connecting to the center. Then this angle is called the latitude angle L. Okay, so from the figure we can see that this latitude angle can vary till these are our poles. So this is our north pole, this is our south pole. Okay, so from the figure we can see that this latitude angle will vary in the positive direction upward to the poles. Similarly, it can vary below to the minus 90 degree to the south pole. Okay, so this latitude angle vary between 90 degree to the minus 90 degree. So can anyone guess that what is its value on the North Pole? You can also write in comment. Okay, so just I'm going to tell that when on the North Pole, this value will turn to be 90 degree. Okay, yeah, yes, Bevo, it is correct, 90 degree. So this is the latitude angle and the sign convention that we use for north, that if we are taking towards the upward angle. Okay, this is, if this is the direction to take the angle, then it will taken as positive. Okay, similarly it will happen when we taking it in the clockwise direction towards the downward, then we take it as negative. Okay, so for towards the north direction, it is taking as positive, whereas towards south we take it as negative direction. Okay, so let's discuss some more thing, that as we know that our sun radiates normally between the tropics, that is Tropic of Cancer and Tropic of Capricorn. This is the region where sun radiates normally. Okay. And if we try to find the latitude for these tropics, then we can easily say that for Tropic of Cancer, the latitude angle will be plus 23.45 degree. Okay, similarly for the Tropic of Capricorn, any point on this tropic, okay, the latitude angle will be minus 23.545 degree. So from this figure we can say that for latitude angle, L 23.45 to minus 23.45, sun radiates normally. Okay. Above these tropics, sun never radiates normally. Although there will be some sunlight, but it will never fall normally to any point above these tropics. Okay, so that is why above these tropics, there are more ice found on these locations. Okay, so now let's move to the next angle. The next is declination angle. So the declination angle, as we know that, suppose this is our globe, this is our center, this is the equatorial plane, and if the sun is radiating like this normally, then this angle with the projection of its on the equatorial plane, that is called the declination angle. And for Earth, this declination angle varies between 23.45 to minus 23.45. And how it changes throughout the year, that I expect you have already seen in the figure, also with the expression. So suppose this is around 1420, this is around 1320, then this curve, sorry, just okay. So the expression for this delta is, you have already seen, plus minus 23.45 and 1 plus sine, some function of sine. Okay, so this delta varies as sinusoidal function. Okay, like this. This is from Jan to December. Okay, this is minus 23.45. This one is 23.45. Okay, if you will take this minus 23.45, then in actual the below point, that is minus 23.45, falls on the 21st December. Okay, so this value will be some lower, that is 23.45, if I am starting from the 1st Jan. Okay, and it will be like this. Okay, so this is the declination angle. Next I will discuss the tilt angle. Okay, so I expect that you have already gone through the derivations that had been done in the classes, also discussed with the another TA. Okay, so in these formulas you have aware that there is a angle that a plane makes with the horizontal plane, that is called the tilt angle beta. Okay, so that tilt angle can vary between beta equal to 180 to 0. Okay, of course it can be equal to 180 or 0. So from this figure we can see that if the beta is greater than 90, that is like, suppose this is greater than 90, okay, and this is the surface, and sunlight is falling like this, okay. And from this the second figure B, you can see that there is no meaning of placing the any collector or panel uh, above the tilt angle 90 degree, okay, as sun is radiating like this, and there is no meaning, okay. So beta greater than 90 degree, we can say that surface has a facing downwards, okay. So you will often see that this beta you will get or will be given between 0 to 90 degree, okay. Let's move to the another angle, that is our angle. I have explained more about this hour angle in the last class, so today I will only tell about the sign convention, okay. So this hour angle varies between omega s minus omega s to minus 2 plus omega s, that is sunrise angle to the sunset angle, okay. So I have taken the project actually, okay. So omega s, as I have also discussed in the previous discussion hour, that after 12 after 12 noon, okay, that is solar noon, we take omega positive, whereas before solar noon omega we take negative, okay. So this omega s will be sunset angle, and here we can say that this one is sunrise angle, okay. Next is the azimuth angle, okay. So the sign convention for this azimuth angle is taken similar to the hour angle, okay. Also this one is taken as positive in the west direction and negative in the east direction. What I'm trying to say in the east or west direction, that you will see in few minutes, that in through a problem, okay. So that's it for the angles, okay. So if you have any doubt in the angle, different types of angle, then you can ask, else I will move forward, okay. Okay, so let's move forward. So now I will start the topic called shading, okay. This is more similar to that we have intuitions for the term called shading, okay. That suppose this is our sunlight, and there is any observer or receiver, then if anything like any building or any tree comes in between this sunlight and this receiver, then what will happen? There will be shading for this building, okay. And this shading will be how much length it will be, it depends on the sun solar altitude angle and different types of angle, okay. So suppose this is the building, then, and this is the angle for the sun, then you know that with this angle this will be the shadow, okay. and this portion of this collector will be shaded. Okay, so this is the basic concepts for the shading. Also we can write that when a object comes in between the sun and the receiver, then there will be shading. Okay, so more often you will find this shading, you will find three types of problems. Okay, the first problem for the shading type is like when that I have discussed about that is the first type of problem. Okay, so I will write when a building or tree or anything, okay, any object comes in between the sir, voice is clear but video not visible. uh, Video or share screen, what do you want to say? Hello Vajnath, could you just write that the what is the main problem? It's like with the screen or the or my video? Video is visible clearly. I was writing.
There are some network problems, sir.
Okay, so I think it will be from your side. The others are
Okay,
able.
sir.
Yeah,
Okay, sir.
yeah, yeah.
Okay, sir.
Okay, okay. So let's move forward. So I was saying that there will you will find more often three types of problems. The first problem is when a
Okay, sir. I will try.
okay, okay. So the first problem is like when a building or tree comes in between the sun ray and the receiver or collector. Okay. The second type of problem you will more often find that suppose there are number of rows of the panels or collectors. Okay, this is more often you have seen in the solar field where what will happen that the shading of the first or earlier arrays falls on the second row. Okay, so this is the shading part. Okay, so this is our second type of problem, shading of collectors. I have written this other than the first row because in this type of problem you have to solve only for the second or third or the later rows. Okay, because there will be no shading because of the previous or sorry behind panels on the first row. Okay, that is why. on the adjoining. Okay, so now the third type problem you will often see is shading windows, okay, by the overhangs. Okay, so this is like, suppose this is any wall, and on this wall this is the window that is placed in between this wall. Okay, and there is an overhang. Then if suppose this is the light coming, then there will be shading on this window. Okay, so this is the third type of problem you have to see in this course. Okay, so now I will start with the first type of problem, that is if any object fall between the receiver and the sun. Okay, before that, this is the first problem that we will see. This is very simple problem. Okay, a PV panel that is at 60 degrees south is 20 meter to the north of a building of height 60 meter. Will the panel be shaded by the building? Okay, so you have to just tell that mm, at this location will the building observer sorry, the panel will be shaded or not. Okay, so as I have also told you earlier that sun radiates normally only between these tropics. Okay, and uh, we take this as north direction and this one as south direction. Okay, now in the problem it is given that the location is 60 degrees south. So first you have to draw the observer receiver position. Okay, that is 60 degrees south. So you know that this one is minus 23.45 degree south. Okay, then this 60 degrees south will fall below this tropic line. Okay, okay, Tropic of Capricorn, that is. Okay, then what is given that this panel is 20 meter to the north of a building of height. North of a building, what does that mean? That the building should be fall south to this receiver. Okay, if this is our building, then we will only say that this receiver is in north direction to this building. Anyone has any doubt in this? Okay, fine. So now you have the figure, and you can see that the sun radiates normally only between these tropics, and the building is south to this panel. Okay, so the sun always will be like this. Okay, either this or this. Okay, so please explain once more. Okay, so I was saying that in the problem it is given that a PV panel is 20 meter to the north of a building. Okay, so suppose this is our PV panel. Then if the question is saying that this panel is north to the building, then what it mean? That the building will be in south to this panel. I am just saying opposite what is saying in the problem. Problem is saying that PV panel is north to the building. I am saying that building is towards the south of the panel. Okay, so in this problem you can see that this is building, and this one is our north direction, this one is our south direction. Then this figure is correct, as the question is saying that PV panel is north of a building. Okay, Ajay, now it is clear?
Sir, I'm still finding difficult to locate that because we are showing the building on a below the Tropic of Cancers, and the North Pole is on the upside.
Okay.
And this panel is considered to be flat on. This is the building. So where is my panel? मैं इसमें locate नहीं कर पा रहा हूँ sir अभी भी.
Okay. Okay. So you have to just go through step by step process. Okay. And also don't think that how the building will be on the pole. Okay, both are the poles, north pole and south pole. Okay, this one is our south direction, this one is our north direction. The problem is saying first
Okay.
that PV panel is located at 60 degrees south. So I have told you earlier that south direction mean towards the downward to the equatorial plane. Okay, so this
Okay.
building first you have to
Hmm.
draw this PV panel. So this PV panel will be placed at anywhere in the 60 direction, 60-degree angle. Okay. So suppose this is our 60-degree, this one is our 60-degree angle. Okay, and this is our PV panel.
Fine.
Then the next what is this? 20, PV panel is 20 meter to the north of a building. Okay. If now you have to say that if I will put the building above this, okay, then this PV panel will be in south direction to this building. Okay, is it clear? If I will draw this
Yes sir.
building above this PV panel in this position, suppose A, then you will find that now in this condition, in this situation, only this. In this situation, the PV panel is in south direction to the building, but that is not correct. You have to show that the building, the PV panel is in north of a building. Okay, so you have to just make opposite to the building that I have
Okay.
drawn. Okay, so now you can see
Okay,
that
fine
this,
sir.
yeah. Okay, so this is our building. Now I was saying that you have find that sun always radiates normally in between these tropics. Okay, so if this is our PV panel and this is our building, then you can easily see and that this suppose this is our sun ray, then this shadow of this PV panel will fall on building. It will never happen that this shadow of this building is falling on the PV panel. For that, what should be the direction of the sun ray? It should be the direction to fall the shadow on the PV panel. And as I have told you that sun never radiates beyond these tropics normally. Okay, sun always falls in between these. Okay, and beyond these tropics there is only sunlight at some angle like that. Okay, so the answer of this problem will be, will the panel be shaded by the building? The answer will be no. The similar you can think for the opposite. If I will say that this building, if I will take any position on the, suppose I have taken any PV panel in the north direction, okay, and the building is in this direction. Now, okay, now you have, you know that, and this is our Tropic of Cancer. Then this shade of this building will never fall on this panel. Okay. Okay. So is there any problem? Okay. So this one is a simple problem that I have told you. Now I will just move to the next problem. Okay. So the next problem is the plan view of the relative position of a proposed solar collector with respect to two nearby buildings is shown in the following figure. The latitude of the location is 45 degree north, find out what hours on August 16 the proposed collector will not be shaded by any of the buildings. Mark Sunpath diagram. Okay, so the first this one is from the first problem that I have discussed. Okay, that when a building fall in between the sun ray and the collector. Okay, so these type of problems is solved by the Sunpath diagram. Okay, I will show you that how it looks like. So this is the figure for the Sunpath diagram, where this one is our solar altitude angle that you have seen like alpha. Also the solar azimuth angle that we have denoted as AS. Okay, and you will see some lines on this graph. If I am plotting these lines, it means for a particular delta I can use this graph. Okay, this one is our latitude, so for this graph changes for with the latitude angles. Okay, so these are the parameters, latitude and the declination angle that I have fixed for this graph. Also in the graph the alpha, solar altitude angle and the azimuth angle is changing. Okay, so these are the variables. So now how I will use it, that we will see with this problem. Okay, so in the problem it is saying that this is our collector. Okay, that is at a height of 10 meter, and these are two objects. Okay, suppose this is object 1, this one is object 2, and these are coming in between the sun ray and the collector. Okay, so I will start with the object 1, that how or what time it will shed to this collector. Then we will move to the second object. Okay, so object 1. So in the Sunpath diagram, I have shown you that there are two variables, that is alpha and Ager, that we have to solve for this object. Okay, so let's draw some figure for this. So this is our building. Also, the height of this building is given. So this is a 2D diagram. If you will see in 3D, I have just make a roughly sketch for this. Then you will find this is like our 3D diagram. Okay, where this is our receiver that is placed 10 meter height. Okay, this is our object 1 and its height is 70 meter. Okay, and this one is uh, 25 meter far. Okay, so this one is 25 meter far from this building. Okay, so what we will do, that we will take some arbitrary point on this building. Okay, so if we are able to find some points on the edges. Okay, if the edges of this building will not shade on this observer, then in between there will be no shading. Okay, so I have taken a1, b1, c1 at the top of the building and a0, b0, c0 at the below of this building. Okay, and the distance between it, the total the total width is 30 meter. I am making these points here. Okay, so if you, this one is our top view. Okay, so if you will see it from the above, then you will find that a1 and a0, both the points will fall on this point. Okay, similarly if I will take this, then v1 and v0 will fall on this, on here, and c1 and c0 here, and this one is at the midpoint that I have taken randomly. Okay, you can take more than one point, but in this problem it is a lengthy problem, that's why I am taking only 3 points, and this one is 15 meter. Okay. So now what I have to do, we have to calculate the alpha and Az. So now I am solving for the first point, that is A1. Okay. So at A1, the distance between the observer and the A1 is 25 meter. So also it is given that this one above towards upward is north direction, whereas towards downward it is south direction. Okay. So if we will try to find the azimuth angle, what is it? It is the angle between the projection of this object uh, with the south direction. Okay. So this is our south direction. So the angle between this projection and with the south direction will be 0 for this A1 only. Okay. So in the at this point A1, the azimuth angle will be 0. And the second, if how we will find this alpha is the elevation angle. Okay. So now I am drawing the side view for this. Okay. So this one is our 10 meter of the collector height. This one is our building 70 meter. Then what we have to calculate alpha. What will be? It is the angle between the observer point with the projection of it on the horizontal plane. Okay, so this one is alpha. So as we know, this one is our 70 meter, this one is our, sorry, this one is 10 meter, this one is 70 meter, and the distance between these is 25 meter. Then this one will be 60 meter. Okay, so by using simple 10 rule, 10 alpha will be 60 by 25. So when we will solve it, we will find that alpha is equal to 67.38 degree. Okay, so what are the altitude and azimuth angle for this point A1? This one is like 67.38 and 0. Okay, similarly we will solve it for the point B1 C1. Also there are two buildings given, that is two objects. Then we have to solve it also for this building, and I will use the points like P1 P0 for this left one, uh, P Q1 Q0 and R1 R0. Okay, so now I will move to the second point, that is B1. Okay, so at B1, okay, this one is our, again I am drawing it the top view. This one is our point A1, this one is our point B1. Okay, what will be this angle? This one is our azimuth angle for the point B1 that we will try to find. Okay, we know this distance, this one is 25 meter and this one is our 15 meter. So you again using 10 rule we can find that this angle AZ will be tan inverse 15 by 25. Okay, and when you will solve this, you will find that this AZ comes out to be 30.96 degree. Also, now in the starting I have told you that towards the west direction we will take the azimuth angle positive. That's why I have taken AZ as positive. Okay, now second, what we will try to find the value of alpha. Okay, so for alpha, first we have to find this value between the B naught and this observer. What we are trying to find, that I am showing here, this distance. What is the distance between the projection of this point B1 and the projection of this panel on this, on the horizontal plane? Okay, this is the length. So you can see that this one is our 90 degree, that is in a straight line. Okay, so this one is our 15 meter, this one is our 25 meter. So we can easily calculate this length, that is, suppose this is observer O, then this OB1, OB0, I should write OB1 will be equal to 15 square plus 25 square, that will come out to be 29.155. Okay, now I'm drawing the side view for this point B1. Okay, I made some mistake. Okay, this is our observer collector O. This one is our point B1. Now what is this distance? Can anyone tell me? This one will be the same distance that we have calculated as OV0. Okay. No, it will not be 10. I am talking about this length. Okay. This one will be equal to the OV0 that we have calculated. From the figure, if you from the 3D figure, I am talking about the side view. So what will be the side view? The side view is like B0, B1, that is this one, and this one. Okay, so what is this distance that we have calculated as OV0? Okay, so this one is our OV0, and this one is similar to the earlier one, that will be the 60 meter. Okay, so now we have to calculate the angle alpha. There we can write alpha is equal to tan inverse 60 upon this length OV0, that is 29.155. This one is our 29.55, 155. Anyone has any doubt that how it is 29.155? If you have any doubt, then I can resolve, else I will move to the forward. Okay, so let's move forward. So when you will solve this, you will find this alpha is 64.08 degree. So the alpha and the Ager value for V1 will be, alpha value is 64.08 and the Azimuth angle is 30.96. Okay. Okay. Now for point C1, that is the most left of this building. So I will draw the figure. This one is our C1. This one will be the Ajamuth angle for this point C1. Okay. This one is given in the problem directly as 30 meter. Okay. This one is 20 meter. So we can easily calculate the Ager value, that will be tan inverse of 30 divided by 25. Okay, and you will solve, you will find that this Ager value comes out to be 50.19 degree. Okay, now we have to solve what will be the alpha value. So again I am trying to show you that first for this C1 what we have to calculate. So, for this C1 what will be the side view? that I will draw in the next figure. Okay, so for side view, first we need to calculate this distance C naught to this observer. Suppose this is O naught, that is the projection of this panel. Okay, and this one is our O. Okay, so for now we have to calculate this C naught O naught, that is not given in the problem. Earlier for B1 we have similarly calculated the O naught V naught. I have written the O. I should write O naught, I think. Yeah. Okay. So this one is O, this one is O naught, and at the bottom this one will be the B naught. Okay. So similarly I will plot the figure for this point. Okay. This one is our O, this one O naught, this one is C1, this one is our C naught. What is this distance that we have to calculate? So from this figure we can see that this O naught, A naught and C naught. Okay, this angle is 90 degree. Okay, so O naught C naught, what we can write? O naught C naught will be equal to under root of A naught O naught square plus A naught C naught square. Okay, so now here I am writing directly that A naught C naught is equal to under root of that is the distance 25 meter square plus 30 square. Okay, when you will solve this you will find that this value comes out to be 39.05 meter. This distance, that will be 39.05 meter. Now we know this, that this one is about 60 meter, then we can easily find that alpha will be tan inverse of 60 divided by 39.05. When you will solve this you will find that this value comes out to be 56.94 degree. Okay, okay, so for C1 the alpha and Ager value will be 56.94 and 50.19 degree. Okay, okay, now so I have calculate all the alpha and Ager value for this object 1. As we know that we have to solve it for both the buildings, so the similar process that I have done for the object 1 we have to do it for object 2. Okay, so I will I have shown already that I have taken 3 points, that is P1 Q1 R1 on this building at the top side, and P0 Q0 R0 are the projection of this point on the horizontal plane. Okay, I will also try to show you that what are these points. So these are our P1, Q1, R1, and these are the projections on the horizontal plane, P0, Q0 and R0. Okay, so first I will solve it for P1. Okay, so for object 2 and for point P1. Okay, I will draw the figure. This is our collector. This is 45-degree angle, and this one is our P1 angle. This one is given as 15 meter. Yes, it is given 15 meter. Okay, so first we have to calculate the Azimuth angle. Okay, so when we will connect this P1, okay, then you can find that the projection of this P1 on the horizontal plane, that is P0, okay, and it connect with the panel at O. Okay, so this OP1 line, the angle made with the south direction. This is our south direction. So this angle will be our azimuth angle. Okay, so this angle we have to calculate. So in the figure, we know that this one is our 15 meter. Also, the normal distance, that is 40 meter, is given in this problem. Okay, so this one is our 40 meter. So suppose this one is our P1, this one is Q1. Then in triangle OQ1 P1, we can easily calculate this angle. Suppose this one is x degree. Okay, then we can say that x will be tan inverse of 15 by 40. That comes out to be 20.556 degree. Okay, so this x is 20.556. Then we can easily calculate this azimuth angle as Ager will be 45 minus 20.556. That will be 24.44. Now you will see that this point P1 is in east direction to the uh, uh, in the east direction. Okay, so we have to calculate this azimuth angle as negative. Okay, so this AZ will be negative 24.44. Okay, similarly that we have done for the last problem, we have to solve for the alpha value. Okay, so I have to show the side view. So for the side view, first we have to calculate this distance, that is OP1. Okay, so this OP1 will be, or I should write more correct as O naught P naught. Okay, that will be under root of this 15 square plus 40 square. When you will solve, you will find that this value comes out to be 42.72 meter. Okay, now you can draw this, the side view. You know the distance between the projection of this receiver O naught, projection of this receiver O naught, and the projection of this point P1 on the ground edge P naught. Then this distance is 42.72. We have to calculate this angle alpha. The height of this building is given in the problem, that is 90 meter. Okay, so this one is our 10 meter, so this above it will be 80 meter. So now we can easily solve that alpha will be tan inverse of 80 divided by 42.72. When you will solve this, you will find that alpha value will be 61.9 degree. So you can write that for P1 alpha is 61.9 degree and AZ is minus 24.44 degree. Okay, so I have solved for the point P1. Now similarly you can solve for the points Q1. I am just writing that for Q1 what will happen, L AZ, that you can easily say that this 45 degree, this is the azimuth angle for the point of Q1. Okay, also the distance is given, that is 40 meter between the observer and the Q1. Okay, so you can easily calculate the alpha value also. So I am not solving it again. I am just writing directly that this will be the alpha value and the minus 45 is the azimuth angle. Okay, now for R1, what will happen, that if you want to solve the for the azimuth angle, then you will see that when you will solve, then you will find this one will be the azimuth angle for this point R1. Okay, so you can now directly understand that this Ager value will be the 45 plus x. Why plus x? Because these triangles, this triangle and this triangle, these are similar. So the angle, this will also, suppose if I am writing it as y, then this y will be equal to x. Then you have to just add 45 degree plus x. Okay, so I am directly writing the coordinates for the R1. That will be 61.9 degree, and this azimuth angle will be negative, that will be minus 65.556 degree. Okay, so now I have solved all the points, that is A1, A1, B1, C1 and P1, Q1, R1. Now what I have to do, I have to impose all these points on the Sunpath diagram. Okay, so this is our Sunpath diagram. I am just writing all the points together, that is A1, B1, C1 and P1, Q1, R1. Okay, so the A1 coordinates is 67.38, 0. For B1 it was 64.08, 30.96. For C1 it will be 56.94, 50.19. Okay, for P1 coordinated 61.9, minus 24.44. For Q1 it will be 63.45, minus 45. For R1 61.9, minus 65.556. Okay, so this one, the first one is our alpha angle, and the second y is our azimuth angle. Okay, so now I will draw all these 6 points in the graph. Okay, so here when we will do it, suppose I'm trying to make first point A1, that is alpha is 67.38, that is alpha correspond to this 67 point, and the A1 is 0. So when you will use the scale and mark it correctly, you will find it will be somewhere here. Okay, this point will be the A1. Okay, second one is 64.08 and 30.96. So 30.96 will be somewhere here, and the alpha value is 64, that will be above this A1. Okay, so this will be come somewhere here. Okay, similarly the C1 point, that is alpha angle is 56.94 and the Ager value is 50.19. So this will be like this, and okay, so these are the points. Okay, for object 1. A1 was the leftmost, rightmost point. Okay, and this one is our leftmost point. So if we will connect these points, that is A1, B1 and C1, okay, then you will find that this area that is falling below this curve A1, B1, C1, this portion or this time, this PV panel will be shaded. Okay, so for this region, whatever is the days coming in under this curve, or whatever is the time falling, that is like 1 p.m., 2 p.m. Okay, so for this time also for the day like 16 August, September 15, October 15, this collector, this PV panel will be shaded by this building. Okay. So this one for the object 1. So now I think you have already approach that why I have taken the left and rightmost point also with a midpoint to make this curve smoother and the limits for this building. Okay. The similarly I will draw these points P1, Q1, R1. Okay. So the azimuth angle for this curve is in negative direction. That is why. So I am just drawing it directly. Okay. Okay. So this will be our P1. Somewhere you will find this Q1 and somewhere R1. And when the similar process you will do, then this portion, okay, for these days, for these hours, the PV panel will be shaded. Okay. So now I will go to the question and we'll see that the question was asking that find out what hours on August 16 the proposed collector will not be shaded. Okay. So on August 16, so for August 16 the line is like this one is for August 16. Okay. Okay, this one is for 16th August. So the line that is falling in between these regions for this time on this day the PV panel will be shaded except these that is this for this time and for this time the PV panel will not be shaded. Okay. So for this time panel will be shaded. Okay, so the time is written like 8 a.m. So you can say you can assume that time is like time is around 8:30 a.m. So you can say that before 8:30 a.m. the PV panel will not be shaded. After that you can say suppose this one is our 11:20 or 30 a.m. Then between the 11:20 or 30 a.m. to the 12 noon the PN panel will not be shaded. After that you can see that after this 2:10 or 2:15 p.m. the collector or the panel will not shade. Okay. So that's all for this problem that I want to solve. If you have any query or problem with this Sunpath diagram or this problem, you can ask. Also, if you have come out to any query in later, then you can write me also a mail or you can ask me in the next discussion.